Hello friends, next topic is a non-deterministic finite automata, NFA. Non-deterministic finite automata means NFA. means NFA. NFA. What is the definition of NFA? Each and every state have zero or more transition on every input symbol. Each and every state, each and every state have zero or more transition on every input symbol, Clear? This is the definition. What is the mathematical expression of this? Machine M contains 5 tuples. Machine M contains 5 tuples. What are the tuples? Capital Q, sigma, Q naught, delta and F. What is capital Q? Set of finite states. What is sigma? Input alphabet. Q naught, initial state. What is F? Set of final states. F is a subset of Q. Clear? Now, come to the transition function. What is transition function? Delta is a transition function. Is it clear to you? Is it clear? Okay, very good. Delta Q cross sigma tends to 2 to power Q. This is the transition function for non-deterministic finite automata. What do you mean by this? Suppose we have Q naught, Q1 states and input alphabet is A, B. Okay. What are the possibility? Q naught on A, Q naught on B, Q1 on A, Q1 on B. There are number of supersets for Q0 and Q1. 5 Q0, Q1, Q0, Q1. What is the definition? Each and every state have 0 or more transition on every input symbol. Suppose this goes to Q0 and Q1, this goes to only Q0, this goes to nothing, this goes to Q1. This is the transition function for non-deterministic finite automata. What is the definition of the deterministic finite automata? Each and every state have exactly one transition on every input symbol. What is the definition of non-deterministic finite automata? Non-deterministic finite automata. Each and every state have zero or more transition on every input symbol. Clear? Clear? See the example first. See the example first. Question 1. Construct a minimal finite automata that accept a language. Construct a minimal finite automata. What do you mean by the finite automata? It's talk about the non-deterministic finite automata. Non-deterministic finite automata. It means by default we consider NFA. By default we consider NFA. Clear? By default we consider a NFA. Construct a minimal finite automata that accept a language that accept a language containing all binary string all binary string where each string start with 0. Start with 0. Clear? Try to do this question. What are the strings present in the language? 0, 0, 1, 0, 0, 0, 1, 0 and many more. Starting with 0. See, this is the initial state. 0, Q1, final state, any number of zeros and ones. This is the non-deterministic finite automata for the given language. See, on Q1, there is no transition for 1. It means in NFA, we cannot take dead state. Clear? If 1 is coming on Q0, there is no move for this. It is not working. Clear? Next. Any doubt? Next. Question number 2. Construct a minimal finite automata. That accept a language containing all binary string where each string start with 1, end with 1, where each string end with 1. Please try to do this question. Do fast. Do fast. Each string end with 1. Okay. This is the Q naught. End with 1. Before 1, any number of zeros and ones are come. See, on Q naught, Q1 have, on Q naught, for 1, there are two transitions. There are two transitions. Clear? Clear? Okay, next question. Question number 3. Construct minimal finite automata that accept all binary strings, that accept a language that accept a language contain all binary string where each string start and end with same symbol, where each string start and end with same symbol. Please try to do this question. Already we have done this question in DFA. Do first. What is the language? I am writing on board. Start with 0, end with 0. Start with 1, end with 1. In between, any number of zeros and ones are coming. 0 is also accepted, 1 is also accepted. This is the language. This is the language. Try to do this question as soon as possible. Do fast. Have you done? Okay. Friends, do fast. Okay, see, this is the initial state. 0, 0 is accepted. Yes or no? Yes or no? One is accepted. Please see. In between, any number of zeros and ones are possible. In between, any number of zeros and ones are possible. Single zero and single one is also accepted. Single zero is accepted. Single one is accepted. Clear? Clear? See the question. See, this is the NFA for this language. What are the number of states for this language and DFA? 5. 5. But in case of NFA, there are 4 number of states. 4 number of states. Clear? Clear? Any doubt? Okay. Next question. Starting and ending with different symbol. Starting and ending with a different symbol. Question number 4. Construct minimal finite automata that accept the language where containing all binary strings where each string start and end with different symbol. Clear? Try to do this question. You know what is the language for this language? This question. What are the strings present in the language? What is the language? Start with 0, end with 1. Start with 1, end with 0. In between, any number of zeros and ones are coming. This is the language for this. This is the strings that are present in the language. Please do fast. Try to do this. Try to do this question. Okay. Initial state. Start with 0, end with 1. Start with 1, end with 0. In between, any number of zeros and ones are come. In between, any number of zeros and ones are come. Please see the diagram. Clear? Any doubt? Okay. Next question. Question number 5. Construct a minimal finite automata that accept a language containing all binary strings where all binary strings containing all binary string where each string contain contain 0 1 as a substring Please try to do this question. String contain 0 1 as a substring. 0 1 as a substring. See, this is Q naught. This one is initial state. 0 1 as a substring. 0 1. This one is final state. Any number of zeros and ones. Any number of zeros and ones. There is no need to give the transition on input 0. Clear? Clear? This is the NFA for the language where each binary string contain 0 1 as a substring. 0 1 as a substring. Next question. Question number 6. Construct minimal construct minimal finite automata that accept a language containing all strings of A's and B's where each string contain third input symbol should be A. When we read a string from left hand side, should be A. When we read a string from left hand side. Please try to do this question and see the difference between NFA and DFA for same language. See, what is the strings present in the language? Third input symbol. First symbol is anything A or B. Second can be an A or B. But third symbol should be A. This is also accepted. This one is also accepted, and many more. See, this is Q0, initial state. First symbol, anything. Second symbol can be anything. But third symbol should be A. When we read a string from left hand side. After that, any number of A's and B's are come. This is the finite automata, NFA, for this language. See the number of states in this question. When we read a third input symbol, number of states are 4. In case of DFA, how many number of states are present? 5. So please note. When we read a specific symbol from left hand side, we read a string from left hand side, we read a string from left hand side, and string contain nth symbol should be specific. Nth symbol should be specific, then number of states in minimal NFA or finite automata equal to n plus 1. Clear? N plus 1. In case of DFA, how many number of states are possible? How many number of states are present in minimal DFA? 5. N plus 2. Clear? Very good. Next question. Question number 7. Are you remember? I told you construct a minimal DFA for the language where each string containing third input symbol A when we read a string from right hand side. Construction of this type, construction of DFA is a very complex, but construction of NFA is easier as compared to the DFA. Clear? Construct. Now, see this question. Construct minimal finite automata. Minimal finite automata means NFA, finite automata, that accept a language containing accept a language containing all strings of A's and B's where each string contain third input symbol A should be A should be A should be A where each string contain third input symbol should be A when we read a string from right hand side. When we read a string from right hand side. Clear? Try to do this question. Please do fast. What is the language? I will write for you. AB can be anything. This position can be anything, but this one is A. After that, any number of A's and B's are come when we read a string from right hand side. Please. This is also known as regular expression. We'll see later. Have you done? Okay. Do fast. See, this is Q0, initial state. This one is A, Q1. This one is A or B, Q2. This one is A and B, Q3. This can be anything, A or B. This is the NFA for this language. How many number of states here? 4. 3 plus 1. 3 plus 1. In case of DFA, how many number of states? 2 की power n, 2 की power 3 means 8. See the difference. When we read a topic conversion of NFA to DFA, then we will do this question, how to convert into DFA. Okay? Write down the note. When we read a string from right hand side and each string contain nth symbol should be specific, then number of states in minimal finite automata equal to n plus 1. Clear? Either we read a string from left side or right side. The number of states are same in finite automata, in minimal finite automata. That is n plus 1. Either we read a string from left side or right hand side. If nth symbol should be specific, the number of states should be same, n plus 1, n plus 1. Clear? Are you getting my point? Next question. Next. Question number 8. Construct a minimal finite automata that accept a language minimal finite automata means NFA. By default, finite automata is NFA. That accept a language containing all binary strings where each string contain 000 as a substring. Contain triplet as a substring. Contain triplet as a substring. Please try to do this question. Triplet as a substring. Okay, see the language. Triplet means 000 or 111. Before 000 can be anything. After 000 can be anything. Plus either this or this. Any number of zeros and ones. Any number of zeros and ones. This is the language. Draw a minimal finite automata for this language. Minimal finite automata for this language. See, this is the initial state, 0, 0, 0, accepted, 1, 1, 1, accepted. Any number of zeros and ones, any number of zeros and ones. This is the finite automata for this language. Clear?